Welcome. Today's topic is moving beyond NI examples. This is a mostly entry level to intermediate level presentation because we don't always have enough of those. If you go back to NI years of decades past, they'd have a lot of entry level and medium level, and they didn't have enough of the high end. And these days it's sort of more the opposite, too much medium and too high end with not enough of the low end. So I'm trying to hit more of the, I've been doing this a little while, but I want to learn some ways to do things a little bit better than I'm doing. A little bit about me. Let me get the mouse over here. Who am I? I'm Aaron Gelfand. I am a longtime LabVIEW user. My first experience was with LabVIEW 5.0, now with Undo. For those of you who haven't heard the history, LabVIEW 5, released in 1998, was the first version where you could undo some of your steps rather than just having to manually destroy things. I am a certified LabVIEW architect. I've been a LabVIEW architect since 2003, so it has been quite a while. I am a LabVIEW champion. I am a doggy doula. I am, this month celebrates 14 years in rescue, and my wife and I specialize in taking in the dumped pregnant dogs. 14 years, 628 foster dogs have been born in my home or spent a minimum of 1 night in it. And you can see those pups love LabVIEW. I'm also a shark. There is an event called Jaws on the Water where you get to watch the movie Jaws while floating on inner tubes in Lake Travis. We put scuba divers in the water to mess with people. I am the head shark. If you're in the Austin area, it's coming back this summer, June 20th and July 18th. You may not see me, but I will find you. Over the years, because I do have 28 years of dealing with LabVIEW examples, there's, for me, a love-hate relationship with them. There is a dichotomy within the examples in that the examples are good for demonstrating tasks. They're good for demonstrating APIs. However, just taking them by themselves, even though they might get you the measurement you need right this instant, they're not really designed to move beyond that for repetitive use, for use in a daily workflow. So they're not really designed to demonstrate behavior in real-world usage. Why are they great? I started my career as an NI, what they now call a TSE, a technical support engineer. Back then we were called application engineers. And in 1999, I was pulled out of my group to do training on two different product lines, motion and image acquisition. And so I wasn't on the phone for 2 weeks. And I'm sitting here doing some of the learning courses when my phone rings and it's got a brand new technical support request number on it. And I'm like, why is it coming through to me? One of my friends from Space Camp, she was continuing schooling, she was going for her master's, and their project had been selected to fly on NASA's KC-135 Vomit Comet. This is Friday. They're flying on Monday, and they're having problems with their program. And of course, it's using NI data acquisition equipment, so it's like, I know him, can he help me? And I'm like, okay, what are you trying to do? I'm like, okay, open this example, let's change this, and 5 minutes in, and we had what they needed. Now, unfortunately, they needed a lot more lead time, so I couldn't take Monday off and go fly with them. But that's one of the very strong things about a number of the NI examples. They are very functional. So they generally work. There's a lot of them that you can turn around and build into an executable. I have a new customer last year that they have some older research programs and it's new graduate students taking over some code that hadn't been updated in 5 or 8 years. And they were all example-based. But there's some weaknesses to that as well. So they generally can be built as executables, but generally you don't want to build them straight as executables because of those weaknesses. And we're going to go through and do some step-by-step modifications off of a real example. What are some of their limits? Poor error handling. They're designed deliberately as anything goes wrong, we just stop the program. That doesn't usually work in the real world for you. Another weakness is poor edge condition handling. They have hard-coded configurations, so if you do want to turn around and build them into an executable, it's always going to come up with the same values every single time, even when those values may not be appropriate. And I have had one customer where they would modify the default values, change them, save them, build an executable named executable 5 volt, change it, built another executable called executable 10 volt, because that was as much as they knew how to do. And so hopefully by the end of today, you'll know to do a bit more. Most of them do not have an ability to save data unless they are designed for data logging. And they mostly don't demonstrate multiple techniques. They're designed to get you up and running to do one thing and one thing only. They do it well, but most people don't need only one thing. So let's look at some specific examples. NI has a toolkit called the STM toolkit. It debuted about 20 years ago as a reference design, and STM stands for Simple TCP Messaging. It was designed to show an easy technique for communicating between two different systems, whether it be a CRIO and your computer, whether it be two computers. Now, I will note that in parentheses, I have this modified version. And that's because when I downloaded a newer version of this, it didn't have one of the problems that I'm going to demonstrate because I had dealt with a much earlier version and have used that earlier version, and they did since fix one of those problems in the design. So I am doing a slight disservice here to the toolkit by saying, hey, it's got this problem when they have fixed it in later versions. So what are some of the problems we have with this reference design, with this architecture? Well, one problem we have here is that a misformed data packet is going to end up terminating your communications. So in this case, you can see we have the unflattened string, and it's got a type definition of what type of window am I using for my filtering. And if you have it's a string, and if you have a typo, it's going to generate an error, and that error is going to terminate our communications. Not very good in the real world, right? Another problem is that the loops may not stop consistently with each other. We start off by initializing a port. We tell some of the internal data mechanisms what are our allowed communications, and then we sit there waiting until we get a connection. Once we have the connection, we have the 3 different loops. We have our host to target message parser, we have our target to host message sender, and we have our data generator. But we can terminate one of the loops and not have the other loops stop successfully, leaving our program in a hung state. Because the communications are string-based, it's very easy to make typos between your server and your client. And they're case sensitive, and they're strings. They're not type defs. Now, admittedly, some of the tools that would make it a lot easier to deal with type defs didn't exist at that time. Again, this is a much older toolkit, but it's one I use frequently still. And it was designed, you don't see it, but under the hood, it's designed that if the messages don't match, you get error codes, and again, you drop your communication. And with this design, they don't actually give you an example showing how to resume communications if they drop. You can have network traffic that causes an interruption in communications. You can have, people walk and trip on cables that weren't secured properly. You want robustness in your real world code. And this example, and a lot of examples, do not provide that robustness. And of course, we also have a bunch of unhandled errors in the example, so that if something goes wrong, you don't necessarily know it's going wrong. And so you're sitting here going, what's going on? And you're never finding the root cause because you never had the code handling the root cause. You're trying to troubleshoot it downstream when all the problems were upstream. In the current version of the toolkit, they do fix one of those. They use notifiers so that if any one of the loops terminates, all of the loops terminate. So I do want to give them that credit that that has been fixed. It was a pet peeve of mine for 2 decades that when I was designing these slides earlier this year, I pulled down a newer version of the toolkit and, oh, they fixed that. For the rest of today, we're going to talk about an example that I pulled pretty much at random of just going into Example Finder called voltage continuous input. The benefits of this particular example program is it shows trying to do continuous data acquisition. And it has the ability to log to disk in CDMS format. However, again, as many example programs, if I want to take this and I can build this straight into an executable, but it's not going to do things like save configuration, so I have to reconfigure every time if it's not the correct configuration. It also doesn't have any sort of range checking, so that max minimum voltage, I can give it illegal values and it's just going to error out. So when we're talking about examples, what are the biggest mistakes people make with using NI examples going into Example Finder? What are the top 5 biggest mistakes? Any guesses? No one? Don't corrupt your examples. Use file save as first. A very frequent mistake is people go in and start modifying the example to do what they want. They make a mistake, they want to go back, they've already saved and overwritten the NI example. And then it's like, oh boy, do I have to do a repair LabVIEW now? And unfortunately, yes, that is something NI is aware of, and they've been trying to come up with a good idea on how to solve it for years, and we may finally see some ideas coming to fruit in the next year or 3. Number 2, don't corrupt your examples. Number 3, don't corrupt your examples. Number 4, any guesses as to number 5? Don't turn your example into a sub-VI. The examples with very few exceptions, are designed as a standalone example of do this. They combine everything into one, and so are very infrequently suited to be used as a sub-VI in another program. Sometimes, as in the case of my friend flying on the Vomit Comet, we need something quick, dirty, and it's a one and done. It's not something we're going to be maintaining. If you have, I've got a team here, I've got a team here, I've got a team here, they all need to do some data logging. In the case of this voltage and continuous example, I need to get something out to them right now, but some of them are going to have different hardware, different limits, and they can type that all in. If we build the example program, a lot of them don't necessarily have a start. Their start is clicking the run button, and that doesn't give you time to actually do any of the configuration, right? Because it's going to run immediately. So for quick and dirty, if the NI example does almost everything you need, one thing we can do is just add an event structure. Move all of your controls to the left of the screen, put an event structure around it, add a start button. And so we see we have a start button, we have all of our controls, because if I just do a start button and my controls aren't inside that event structure, what's gonna happen? LabVIEW is gonna open, it's gonna read all these controls. It might be waiting on the start button, but you've already read everything, so any user interaction that has been done of changing your settings is ignored because LabVIEW already read it. We want to make sure to place all of our controls to avoid that error. In this case, it supports data logging. We have the DACMX configure logging. And to make it nice for the user so it just doesn't leave our panel open afterwards, is we want to exit LabVIEW. Everyone's familiar with the exit or quit button? Generally what we want to do though is we don't want it exiting every time I'm modifying my code, right? So two easy ways of dealing with that are to use either a conditional disable structure for runtime engine equals true, and runtime engine equals false is when we're in the development environment. Runtime engine equals true is when we're in an executable. We can put that there and we don't have to worry about LabVIEW quitting on us every time. An alternative approach is to drop a property node, set to application, and you can have application kind that gives you runtime system, development system, invalid, a couple of others, and we can just put our exit in that case structure right there. When do we do this? Preferably never. This is saying I don't have time to write real code. I'm in so much of a hurry that I do need to distribute something to multiple sites, and I'm going to take an infinite amount of technical debt to just get this done once. So when you have no other choice, data is needed now, a solution is needed now, and there is zero expectation for the code to be maintained. I've been there. I've been there in the lab at midnight with people around the world needing something. So sometimes that's what you have to give them. But realize that you are taking on a large amount of technical debt in doing that. And so for a demo, let me get the VI open. You know, here I've taken my voltage continuous input measurement and I've added my event structure. I've moved all the controls all the way over to the left versus where they were in the original. And just to show you that I'm not, where's my mouse? What I did on this project is notice the very first thing I did was saved my example as number 1, the original. I've got a copy that I'm keeping, my own personal copy for this demo is my original. And then my number 2 is my quick and dirty. And I named it number 1, number 2, number 3. And this gives us an executable that we can build quickly. It's not very maintainable, but it gives us the I needed something done yesterday approach. Let's try and move beyond this. So when I talk about architectures for today, we're taking a very simplified approach of talking about architectures. Again, as I mentioned earlier, this is sort of a beginner level course. So for purposes of today, we're going to talk about 3 variations: run and done, which is what we've just seen, and we are done talking about run and done. State machine, which is going to be the remainder of the demos. And we're going to talk about queued message handlers. Queued message handlers is when you really get into good level architectures, and we won't really be talking about that much today. We're getting you to the intermediate step, not to the expert step. If you had attended LabVIEW Core or LabVIEW Basics a decade ago, 2 decades ago, they talk about AAP, acquire, analyze, present. That is what our program is supposed to do. I'm going to suggest we actually consider a variation of that, which is our program needs to support configuration. We still have that acquire, analyze, and present, and then we have to do cleanup at the end. So let's talk about configuration. Configuration for a program generally has 2 sources of information. You might source your information from a local file. You might source your information from a database. When you're trying to figure out what is going to be in that configuration file or database, the information you need can vary. There's some things that you just, you hard code a timeout. You hard code this, you hard code that. When in doubt, if you ever think you might need to change it, make it a variable to begin with, and you're going to be a lot happier. That you're not going to get downstream and figure out you've deployed it to a couple of the labs, and one of the labs has an older, slower device, and now you have to rebuild everything for everyone. In the GUI, to make it easier on your users, disable what configuration items are not relevant to the mode of operation and to the user. A test operator may be allowed to configure a much smaller subset of information, or may have access to a much smaller set of information than an administrator. Also, when you're dealing with this, think about what happens if that configuration file or database gets corrupted. Many times over the years, I've seen the file get corrupted. Now the test operator is stuck. They can't do anything. And it's like, okay, what's next? I have a reuse library I use on a lot of my projects that gives me easy ways to configure. And one of the requirements as I start saying I'm going to have this data item, this data item, this data item, is I actually have to give it a default. And anytime that file gets corrupted or deleted, my program will automatically regenerate back to the defaults. The defaults are hard-coded into my program, but only used if the configuration file doesn't exist and has been corrupted. Also, one thing, because I have seen this, is unfortunately something you do have to think about is if your test limits are going in the config file and you're on a manufacturing floor where they care more, where test operators might care more about passing rather than passing reliably, who has access to that file? Where is it stored? And do you have to do things like encrypting certain pieces of information in it to prevent it from being modified in a text editor? Something else you have to worry about is, can your resources or identifiers change? An example I'll give is the NI USB to RS-232 cables. I can plug one of those in. It enumerates in Windows as COM5. If I unplug it and plug it back in, is it still going to be COM5? I've got a shrug. The answer today is yes. For the NI USB cables, it is. They will re-enumerate to the same one. But if I plug in a different NI USB 232 adapter, it will get a different COM number. Windows allows tracking by device identifiers and additionally sub-tracking by serial numbers. But if your driver doesn't choose to implement that sort of option, then every time you plug in the same device, it's going to be COM4, COM5, COM6, COM7, COM8. So we can play tricks with our programs. So an example I have here is I'm doing a DAC-MX system call to get all of the DAC-MX devices attached to my system right now. And I'm then doing I'm iterating through my active devices and I'm trying to find the product type to find my NI9476. The 9476 is a CDAC module. It's a 32 channel, 24 volt digital out. And so putting this in my code rather than just saying CDAC1 module 1 protects me from plugging a different 9171, which is a USB to CDAC carrier, with a different 9476 in, because if I plug a second one in and it got a different serial number, now it's CDAC2. And if I've hard-coded that, or if I've coded that into my program, then, and I just had to do a hardware swap out, or I'm on a different station, I don't have to worry about having a different configuration for every one of my systems. Now, there are some limitations with this approach. If I need two 9476s in my system, it doesn't work. But these are all tricks that, as we're starting to create our own more robust programs, these are all tricks that we learn. Illegal configurations. Are the defaults valid for devices you might be using? I have, for purposes of today's demonstration, a NI USB 6008. It's a little cheap. It was designed as one of their value products. It's a little cheap USB DAC device. It has 8 analog inputs, 2 analog outputs, and a number of digital I/O and some counter timers. This is the regular NI example for AO voltage outputs. It's an example program. If you try and run it with your 6008, it doesn't work. The reason being is our AO voltage configuration VI has inputs that are not required for maximum voltage and minimum voltage. They default to 0 and 10 because the vast majority of NI products have 0 to 10 volt outputs for analog. Not all of them, but most. The 6008 is 0 to 5 volts. So what happens when we're using defaulted values, either from VIs or because we have defaulted values? How does your program respond to that? So another way we can get around this is we can query our device. You can actually get, if you query, and that's actually a bad example that is the right example. The NI9425 is a analog output voltage module, and you can actually query the input ranges and the output ranges. So instead of relying on users to set up information, get the information from the device itself so that you can allow them to select from the correct values. They don't have to know that this module is 0 to 5 volts and this is 0 to 10, and that I just, if I'm giving a program to 5 different labs that have 4 different sets of equipment, one of the labs is fortunate enough to be the same, that I don't have to memorize all of it. I can query the instrument and provide that information to my user. So we're going to talk a little bit more about acquire, analyze, present. I'm not going to go too heavily into these, but in terms of acquisition, how fast am I acquiring? What type of data am I acquiring? Am I acquiring mixed signals? Is all going to impact your program and what you're displaying to the user. Do I need graphs, or do I need scalar values that are saying the current temperature is 5 degrees? Some operators might just need to know that right at this instant, it's 5 degrees. Other operators, for a test, need to see what is the trend of my temperature. They do need to know the current value, but they also need to know what is the trend over time. Analysis. What analysis is done? How performant is that analysis? If I'm just doing something like a mean over a couple of values, it's fast. If I'm doing a bunch of image analysis, I might be acquiring images faster than I can actually process them, or at least process them if I'm processing them one at a time. If I can take advantage of a GPU, if I can take advantage of the fact that I'm on a multi-core processor and move and do a different piece of image acquisition on different processors so that I can acquire but send off to multiple analysis engines, that's all things we think about. And it's all things that generally are not going to be what I'm looking at a single example. Presentation. How do I emphasize what the user needs to know? How do I avoid information overload, but how do I give them everything they need to know? And it might be, how do I hide what the user doesn't need to know? Because users might need different information. This is a GUI off of a system that I maintain for molecular beam epitaxy, and this is the operator view. The operator, when they're not in semi-autonomous mode and they're needing to do some manual mode operations, can move an arm between the X0 position, the X1 position, and the X2 position. They can also move it vertically between the Y0 and Y1 position. They have the ability to home it, and if something's going wrong, they have the ability to stop it. An administrator of the system, however, might need the ability to jog it, recalibrate it, and so they get more information. They get to see what is the step count in the motor, what is the voltage of the sensor confirming where the motor is. They get to see the step points for the Ys. They get to see a lot more information because they have different requirements. And we can do things like disable in gray, which puts it there and says you're not allowed to modify it right now, but we want to avoid information overload when that information is not relevant to them. Error handling. Error handling is a topic that could easily be a day for discussion items. So we are going to talk about a couple of things, but not, unfortunately, as much as I'd love. In error handling, there's generally a couple of approaches we can take. We can recover and try to do something to resume, or we can terminate. We can enunciate problems. So those of you familiar with the simple error handler and general error handler, that's a form of enunciation. We're advertising it to the user. We're not actually doing anything with that information though. I mean, we might give them the ability to terminate the program, but all we're doing is enunciating. You can design your code to respond to and handle specific errors. And again, very big topic in and of itself. We want to cleanly terminate on errors. When you look at a bunch of the NI examples around output, error happens, and what do? You close your task, and you do your enunciation. What you're not doing with that is trying to safe your system. The examples are designed, an error happens, I'm stopping. Well, an error happens, maybe I need to turn this generator off, I need to turn this load cell off, and I need to do things in a specific order. And that's not what examples show you, unfortunately. Some different things to think about as we're writing our programs. Pathing can vary for your development environment versus your runtime application. I see lots and lots of headaches around this. For example, a user might be setting up, hey, I want this file name. And they include an illegal character in the file name. They put it in they have a typo as they type it in that puts it in a different path that doesn't exist. a lot of these things are things you can program to safeguard the user. There's a VI called recursive directory create. If they're putting it in a directory that doesn't exist, you can create it for them. You can also just do your own data entry that allows them to create the file name, and that you use the event structure on key down and get rid of illegal file characters. You can force what directory they put it in and only allow them to change the name, or you can auto-generate the names for them. And then they can't screw it up. Also, what happens if a physical wire on my system gets disconnected? Assuming we're doing analog capture, some NI devices and some third-party devices are designed such that the input floats positive and then you overrange. Some of them will go float negative and underrange. And some of them just float and not in any given direction. And so you can be sitting there having this value that you don't even realize isn't a real value. So you want to know your system. So now we're getting into the demos. And what we're going to do is we are going to go ahead and take we're going to take that voltage continuous input, and we are going to, we've already done our quick and dirty. Let's start a couple of things. First, we're going to turn it into a state machine. And so here, what we've done is we've created a for loop. We've created a type-defined enum that tells our system what are the states of the system. The states are initialization, our idle, our initialization, our acquisition, and let's quit the program. And so we've taken, and let me get my original back up. Not quick and dirty, voltage continuous input. So again, here is the original NI example that I remembered to save a copy of. Again, I've done it myself, I admit it, but very biggest mistake people constantly make is not saving a copy and corrupting their original. So the first thing we have our we have our configure, we have our sample clock, we have our data logging, we configure our triggering, and we start and loop our acquisition, and we terminate. So that's our original. And so what we've done is we've taken this, in our idle case, we have an event structure that's basically waiting for the user to click the start button. Now, unlike the example, we've also gone ahead and added a stop button. So that will go ahead and stop. And so we're just sitting here generally waiting for the user to start the program. Now, when they click start and I do my initial acquisition, I come here. I have shrunk the code down to fit on the screen better. Don't have quite the same spacing, but here what I've done is just taken that exact same example code, moved it a little closer, and I'm gonna just use it as it is. But what I am going to do is this number of samples gets used in a couple of places, and so I'm passing it out as a shift register. I'm using this as an indicator of knowing that our program is actually acquiring. So when we go back to our idle state has a timeout, and I've got it as 10 milliseconds, so pretty responsive while still saying I'm not going to overload my CPU on idle. And in the timeout, if the number of samples isn't equal to -1, because we've told it to start acquiring, I go to the acquire state, I'm going to acquire my data, I'm going to come back to idle, check to make sure the user hasn't pressed the button, and I'm going to flip-flop between these two states. And if this value is -1, we just keep circling around the idle case every 10 milliseconds. And so I can go ahead and let's move the front panel to this side of the screen. I can start running it. I can choose my module, and I can start acquiring data. And yeah, I don't have anything wired. Now, I've also built this one into an executable. But we said, NI examples don't generally have much in the error handling. So what will happen, and I'm going to do this, I unfortunately shouldn't have started running this from development environment. I should have done the executable first, because if I do the demo I was supposed to do, 50-50 chance I'll end up black screening my computer. So I'm going to do it at the end just in case I do black screen. With this modification to the example, and we'll close it. What do you think happens, actually? Let me start going again. With general, if I go ahead and unplug, my program stops. And my program can never recover. My program's terminated, it's done. So let's start looking at making this a little more robust and reliable for us to be able to handle scenarios like that. The next thing I'm going to do is I'm going to start by improving our error handling. So our program looks exactly the same as it just did on the front panel. Our block diagram is where we're going to start seeing some changes right now. Now what we've done, and I gave myself some notes so that we can make sure that we see them, is in my initialize acquisition case, I don't automatically go to acquisition. I don't know that I was actually successful in the previous version. We don't know that we were successful. Here, we go ahead and we say, if error is true, we just go back to the idle case. We weren't successful. There's no reason to continue and try and throw up bad data. And if we were successful, meaning there was no error, we can go ahead and start. So we make an error handling change here. And in the idle case, we also make an error handling change that says, if our number of samples was greater than 0, meaning we're trying to acquire, we're going to either go to the acquire case, or if there had been an error that comes back around, we're going to go back to our initialize acquisition case. We're going to attempt to reinitialize on failure. And so what that looks like in practice is, again, I select my channel, I start acquiring. Now, when I disconnect my module, my program stopped. I didn't get the error message, but I plug it back in and I'm immediately reacquiring. And so when you're doing like a plant monitoring type situation, you don't want your program to stop because you lost connection to a certain sensor. Especially, and you don't want to have to restart your program once you've fixed that. So that's one basic way of improving the error handling is reinitializing. Now, we can also do things such as presenting the better information to the user. Tab control. How much of the configuration information is relevant while we're acquiring the data? So here, what I've done on the block diagram is I've added a tab control, and when we start our attempt to acquire, I switch my tab control to my acquisition tab rather than my configuration tab. And when I stop, So now I've got all my data much larger. I don't have all this extraneous data for my user. And I clicked stop, and we immediately went back to configuration. Very simple, very straightforward, and a bit more user-friendly. The next thing I'm going to do is add some validation. With different modules, we have different ranges. Here, if I had set up a value of, let's say, 1,000 volts, which this module isn't capable of, and said start, look what's happening with my start button right now. I'm not allowed to start. I have a value that I know is going to give an error, so I'm not even going to allow my user to continue until they fixed it. So I can bring this back to 5 volts, click outside of this, and in this case, I'll also have to switch to the appropriate module, and now I've got a valid configuration. Now, ideally, you don't just want to have that stop button or start button disabled and not have any information to the user why. And so that's when we start doing things like little triangles with the exclamation in them next to the value that is illegal. But again, this particular approach right here, again requires that you know which of these are valid. Our reference single-ended acquisition is valid for this module. Non-reference single-ended is not. But that requires me to know it, or at least for me to do a little bit of an indicator telling the user why this is invalid. Now let's continue making this user interface a little bit smarter for our end user. And let's give them, instead of having to type the range in, let's give them valid ranges. And I have a couple of simulated instruments configured in NIMAX in addition to my actual instruments. So with the 6008, I can query the device, and my valid ranges are -1 to 1, -1.5 to 1, or sorry, -1.25 to 1.25, -2 to 2, -10 to 10, 20 to 20. And so now I'm guiding my user as to what's actually valid. And if I go ahead and do this for CDAC 5 module AI0, which is a simulated NI9425 analog module, we see that my valid ranges are -0.2 to 2, -1 to 1, -5 to 5, -10 to 10. I'm guiding my users to make less mistakes and safeguarding my users. And that gives me a better program. And depending upon whether it's an NI API or you're using other devices, you don't always have the ability to query that information. But at least a lot with the NI devices you do, and a lot of external devices you can get information. You just have to read the manual to figure out, how do I get this information? Not all instruments, unfortunately, support that. Another place that frequently people overlook in terms of that information is querying the calibration date of your instruments. Some programs, you don't really worry about how calibrated your instrument is. but some are very, very, you need very good accuracy. You need that traceability. And so when I'm doing a test system, I usually have on my up on my file menu, I have the ability to say, hey, give me the calibration dates on all the instruments. And for devices that need a 1 year, for NI devices, you can query their calibration interval of how often are they supposed to be. And so you can go in and say, hey, you were last calibrated at X date, your calibration due date is Y. And so like there was one tester that the company said, we do still want to be able to test if it's out of calibration. And so I implemented that. But at 90 days, there was this big red flag that says, hey, your calibration is due in 90 days, 89 days, 88 days, 87 days. And it was a yellow flag. And at 30 days, it became like an orange flag. And at 0 days, it's a red flag. But they said, you're going to allow it to keep testing. And that's what I did. And that engineer left the company. And like 3 years later, I got a call saying, hey, we've been testing for a while, and we hadn't realized it went out of cal. And we sent the device back to NI for detailed calibration, and they said it was way out of cal. Did we ship bad units? And they hadn't wanted this computer onto the IT network because it was a hassle, but I had logged everything, all the test results into a file anyway. And I was able to go into those files and say, hey, based on this error accuracy from NI, based on these values that we actually measured, here's how much we were off by. You didn't false pass any bad units. So as developers, we really want to try and protect our end users in spite of themselves. And so that's all things that we take from that when we're starting at the example. An example doesn't give us any of that. An example shows a task. It's up to us to take the task to reality. Places you can go to next. State machines are outgrown easily. They're the intermediate step from going to tasks, to going to a program, to what's called a QMH, or a queued message handler. And that's where you go next. Any questions? Have I given you things to think about? No questions? I mean, there's only... No? Okay, other events. Oh.
Yes, I do have a quick question. So, this might just be my ignorance with LabVIEW, but you mentioned user control. So, like, being able to, like, okay, just the distinction between, like, a technician versus someone who's a bit more experienced or needs wider permissions.
Yes.
Is that in LabVIEW, or is that across, like, multiple different NI kind of? So,
the question is, trying to distinguish between technicians, operators, engineers, administrators, and are we doing this solely within LabVIEW, or are we doing this across platforms? And the answer is it can be either. Over the years, I've done projects that are pulling Windows Active Directory user permissions of who is the operator logged into this test system right now, what permissions do they have, and the system adapts on the fly. And that information might be across whether you're in LabVIEW, test stand, Diadem, because I know you're asking questions about Diadem at our experts bar. And sometimes you're going to that organizational level. And other times that level isn't needed, and it's just as simple. The screenshot I gave of that operator interface in the slide of operator versus admin, there's two levels on the system. It's file login Control L is the keyboard shortcut in this case that I actually implemented. Type in the password and now you're an admin. And an admin can do certain things the operator can't, but an admin is actually prevented from doing certain things an operator can in that case. There's certain features that we deliberately disable for the admins. They get more information, they get the ability to do certain things the operators don't, but they actually, it's deliberately designed. You have to log out to be able to do certain things. And in that case, it's just, for all intents and purposes, a LabVIEW 2 functional global variable of I have this user level and a simple keyboard entry prompt of, please type in my password. That system has a touch panel, so we do have to have our own little keyboard, but because they didn't want to use the Windows keyboard, because it's also a multi-panel system, and the Windows keyboard, at least we never figured out a way to get it onto the correct one, on the correct monitor programmatically. And so we have our own keyboard to handle the touch screen. But that question, it's a good question, and it's application dependent. For a lot of people, having to involve IT of saying, give this user these permissions, this user these permissions, these user these permissions, is overkill. There's a lot of applications that it's not overkill for it. So it's very application and your need dependent.
Sorry, quick follow-up. Is user management handled locally, or is that something that you can actually hook up?
Again, it can be both. It's dependent upon the particular needs of the organization, and you're going to be seeing changes as with all the focus on cybersecurity these days. But it is do you need that level of security, or is it just enough to have a single password to go from operator to admin? One thing we're also supposed to plug is the GDevCon events. I'm sure you've already seen them plugged in your previous presentations. They are great learning events. GDevCon India, they had their inaugural event last month. Awesome, standing room only. They outsold their availability. GDevCon NA has been going on 5-6 years now. It'll be July in Chicago. They moved to Chicago last year after several years in Boulder. Great venue. GDevCon Europe was the original GDevCon conference. Everybody else is offshoots from them. And GDevCon Europe has been running for years. And we have 2 new ones also coming up, GDevCon Melbourne, Australia, and GDevCon in Mexico, GDevCon Latin America. And so you've got the one coming up in Leon, Mexico in November. Thank you for your time and attending. Oh, I had that one extra demo. Let's see if I can do it without killing my machine. I built just the state machine version into an executable. And if you remember, the state machine version doesn't have any of the advanced error handling. And so in this case, by default, I never ended up implementing, because of time, any types of remembering configurations. So by default, it always comes up with dev1 AI0, which doesn't actually exist on my machine. So if I go ahead and click start, what do you think's about to happen? Kaboom. And what does the operator think at that point? They're like, what the heck? Where'd my program go? And then there's also the variation of, I can go ahead and start it with the correct one, so we're actually getting data. And again, kaboom. What happened to my system? I have no way of knowing. My program doesn't exist anymore. And that's another weaknesses in the examples. And perfect. It looks like I'm ending exactly on time. Thank you very much.
Thank you. Thank you.